Um, categorical data, multiple categories of categorical data. Remember yesterday, this is that fine line. You can do a two-proportion z-test when you have two categories. Remember I showed you guys that yesterday, color orange versus the color yellow or something like that. But if you're talking about all categories, you need to do the chi-square. So just a heads up between two proportion z and the chi-square. Categorical data, what else do we need? Sufficiently large, we'll check that in a second. That's if expected cell counts are greater than or equal to 5. So we should find our expected cell counts in this case. Our expected cell counts will be, if there's 200 people and I hypothesize that 35% are in the 18 to 34-year-old demographic, then my expected value, this is my actual data here, my expected data will be 200 times 0.35. And that should make sense. 35% of 200, and I don't know what that is. 70? And then my expected value over here for the 35 to 64, that'll be 200 times whatever I hypothesize, which is 0.51. What's that? 102. And the next one's going to be 200 times 0.14, which we got, what, 18? 28. Missed the digit there. 28. Each one of our expected cell counts is greater than or equal to 5. So that checks out. We are sufficiently large. All expected cell counts are greater than or equal to 5. And our third one, it was given in the context of the problem. Assume that this is a representative of a random sample, right? Suppose that the data resulted from a random sample. Data is from a random sample. So that's our big three. Those are our assumptions, our justifications as to why we're doing what we're doing. Step 6, chi-square. That is the sum of observed minus expected squared divided by expected. So you can list it by hand if you'd like. It's pretty easy to do by hand. 36 minus, what was it, 70 squared, I think it was, over 70 plus, yeah, and then 102. And observed there was 130. We can dot, dot, dot. You might as well get all the pieces there. Uh, 34 squared. And that's expected is 28. Okay? And we said in your calc, some of you guys have to do it by hand because your calc doesn't do this. So it's up to you. In your calc, whether you're going to use the calc button or not, you still need to put the observed in list 1 and expected in list 2. So, and that was 36, 130, and 34. What was it? 70 and 28. Okay. At this point, I'm going to go ahead and do it by hand again, just to show you guys how to do it by hand. We go to list 3. We're going to make list 3 list 1 minus list 2 squared divided by list 2. That's observed minus expected squared divided by expected. So I will say list 1 minus list 2 squared, and I'm going to divide that by list 2. And then we're going to sum that. You can see that we're going to have a big chi-square value because it's going to be the sum of these values. It should make sense that we're going to have a big chi-square value. Why? There's a big discrepancy than what's supposed to happen and what actually happens according to this data. Does that make sense? So we should also in your brain say, this is going to be evidence that they're different, right? Okay. So we'll sum that up and get our chi-square. So we just need to sum up list 3. And we get 25.486, okay? So your chi-square statistic in this one is 24.86. Again, 87. A reminder, don't want that one, sorry. A reminder that your degrees of freedom are categories minus 1. In this case, we have 3 minus 1 degrees of freedom. So there's 2 degrees of freedom. And our chi-square value was, what, 24.87, something like that? I was way off. 25.48. Okay. Perfect. Dude, get down. All right. Yesterday I didn't show you this, buddy, because I just discovered it today. Go to distributions, second bars. That's where your distributions are. We have used inverse norm, inverse t, and normal CDF. Go towards the bottom. Geometrics, Poisson we don't do. Binomials in this class we have covered, so you should be comfortable with all these distributions at this point. Now there is a chi-squared CDF. Okay? So if you want to get your p-value by hand and not use that chart, it works just like the t CDF does. Lower, comma, upper, comma, degrees of freedom. Our chi-square, remember, chi-squared is one-tailed always to the right. So the scripting for chi-square CDF will always be your value, which was 25.863, comma, upper, give it a big number, 1,000 is fine. That's our upper bound, comma, and then degrees of freedom. In this case, we've got 2. 4863. It's not going to make that much of a difference. I think it's essentially 0 anyway. Hit enter. And it will give you the actual p-value there. So you can do it. All the calcs have that one. Again, notice that this is going to match if I go stat, test, and the TI-84s have the goodness of fit, but the 83s don't. List 1 is observed. List 2 is expected. My degrees of freedom in this case is 2. We're going to hit calculate. And again, it's essentially the same p-value. So there's multiple ways to find that p-value. Does that make sense? And it should fit with your norm CDF as well as your t CDF. Any questions about the p-values there? All right. So that's going to be p-value is approximately nothing. So p-value versus alpha is less than or equal to alpha. 0 is less than or equal to 0.05. That's going to get us a reject. The null hypothesis. And our conclusion. At the 95% confidence level, there is sufficient evidence to say at least one of these proportions is incorrect. That's all you need. Okay? You don't need to specify what proportion is incorrect. You just need to say at least one of these proportions is incorrect. You can put it in context if you want. The portion to 18 to 34-year-olds or 35 to 64 or 65 plus, at least one of those proportions is incorrect. Okay? You guys okay with that one? So that's yesterday. Going to go ahead and get into today's, which is chi-squared for homogeneity and independence. They are the same. Notice that we're going to change a little bit about how the categories work. Basically, yesterday, goodness of fit, here's the best way I can talk about it, because this is one of those small areas that defines whether you get a 3 or a 4 on an AP exam. if you do the right test but don't name it correctly. Okay? Yesterday was goodness of fit. The best way that I can describe a goodness of fit is that it has one and then it has, that's a pen that's not working very well. Okay, it has one and then it has different categories over here. So we got whatever. It's just got one row and column, or one row, if that kind of helps. Now look at today when we're going to test for independence or what's called homogeneity. If you look at our data sets, and I'll go real quick, notice in this case we have a 2 by 5. Does everybody agree when I say 2 by 5? 2 by 5. This is a 1 by 4. Everybody agree with that? Okay. Whenever you have a 1 by something, it has to be a goodness of fit. Once you go away from a 1 by something, you get into something like a 2 by 5, or, where's my next one? This one's a 4 by 2. Okay? Notice we're not a 1 by something. Does that make sense? This is when you're going to use one of the other tests. All calcs have this test. And you guys should know that just some of the calcs have the goodness of fit. But you know how to do it in the columns. This today is a little bit kind of funky compared to what we did here. We won't use lists today. We get to enter the matrix. How many of you people have heard the word matrix in math, not in terms of the movie? Oh, never mind, I'm out.
I was like, oh.
I know the matrix. Today we're going to enter the matrix. What is it, the blue pill? The red pill? Matrix?
Oh, it's the red pill.
Is it the red pill to exit? What's red? The red pill takes you in, the blue pill takes you out, right?
Yeah.
So we're going to take the red pill instead. We're going to enter the matrix.
Yeah, that'll be actually.
All right, here we go. Assumptions. Categorical data. Independent random samples. We're going to be kind of testing for independence. And you're going to see something. You're going to have to clear your heads and go into the Wayback Machine. Back when we tested for independence, you should see a connection here. So random, sufficiently large. Oops, don't want to do that. Don't want to edit it. Sufficiently large, and then categorical data. So same 3 assumptions as yesterday. Okay? To find your expected cell counts. To find your expected cell counts, they will be done differently in this case. Okay? Expected total. Expected values are the row total times the column total divided by what I call the total, and I'll show you guys that in a second. Okay? Row times column divided by total, if that helps. Just row total, column total, divided by total. Yesterday's, it will always be this when we go to the 2 by 4s or the 3 by 3s or the 2 by 7s. It will always be this way to find the expected cell count. On the goodness of fit, there's multiple ways to find that. Remember yesterday, one of them we had to divide it by 6 because we said they were all the same. The example I just showed you, we had to do like 35% times 1, 17% times 1, 18% times another. I don't remember those numbers, but I'm just saying you have to do it differently. Does that make sense? Okay? So today's expected cell count, when we move into the matrices, you do need the row total, column total divided by total. Here we go. A survey was done to find out if dentists should advertise. The following results were recorded. Test to see if there is no difference in the opinions of consumers and dentists. In other words, dentists may be saying something like, you know what, I don't think we need to advertise. People are going to come to us no matter what. Do we agree? Do you see that that's the dentist's opinion looking at this survey? So we're looking at dentist row, and they're saying something like, you know what, hey, should you advertise? Most dentists are saying, if you look at it, a majority of them are saying, no, I don't need to advertise. Does that make sense? Whereas they asked the consumers and they said, hey, do you guys think dentists should advertise? Because if they advertise, they might come, you know what I'm saying? And the consumers have said, if we just look at this data roughly speaking, it looks like there's a difference between the opinions between the consumers and the dentists. Does that make sense? So it does matter. So what the chi-square is going to do is it kind of validates, again, statistical evidence to say there is a difference. Does that make sense? And so the thing that we're looking at here is independence. Are these two ideas independent? Okay. So what we have to do, it's the same kind of setup as before. We're looking at true proportion. And this one's a little bit more generic in how you set it up. And we're going to say something like this. We're going to go, I'll come back to defining it. I got to remember what my null and alternative hypotheses are. Opinions. So we're looking at difference of opinions. So we're going to say, we're going to assume in this case there is no difference. And this is actually going to be a test for homogeneity. No difference in opinions of dentists and, is it hot in this classroom at all?
Yes.
Okay. It seems like it's really hot here. Dentists and what's the other one? Consumers? Are you guys okay if I prop open the door?
Yeah, sure. No difference in
Ryan.
of dentists versus
Okay. Null hypothesis, no difference in the opinions of the dentists and consumers. I'm just going to put dentists / consumers here. Okay? And the alternative hypothesis, obviously, if there's no difference for your null, the alternative is going to be there is a difference. Of dentists and consumers. And yes, in this case, visually, and this is where stats takes over, visually we see that there's a difference because the numbers differ. Is that difference statistically significant or not? That's what we're testing with the chi-square. Now, yesterday we were goodness of fit. Does our data match what it says or we hypothesize to be true? That was yesterday. Today, we're doing a test for either homogeneity or a test for independence. Right now, listen carefully, we know that the word homogeneity means what? Same. So we're doing a test to see if these opinions are the same. So if you're checking for same or different, that's the other name I call the homogeneity test. Homogeneity means same. I'm looking for evidence to say that they're different. That's the alternative hypothesis, same or different. Homogeneity. That makes sense? Alpha level here, did it say? So we'll go with 0.05. We're going to use a chi-square test of homogeneity here. I think it's I before E, right? Homogeneity? EI?
no, it's I think
Is it?
Why is EITY?
Did I spell in the notes?
Yeah,
EI?
EITY.
All right. You know me in spelling. Chi-square test of homogeneity, again, on an AP exam, if you're doing a chi-square test, there's 3 chi-square tests. Yesterday, goodness of fit. Today, test of homogeneity. Tomorrow will be test of independence, but we'll get to it a little bit today. Does that make sense? So identifying the names is like one of those half-point deductions. You can get almost full credit. They still will deduct you if you don't name it correctly. Yes?
Do we have to mention what we're talking about, like proportions, like for the null and alternative hypothesis?
Your step 1 here actually is not necessary. You can write something if you want, but technically there's multiple proportions. You'd actually have to say the proportion that strongly agrees is the same for consumers and dentists. The proportion that agrees is the same. The proportion that's neutral is the same. You know what I'm saying? So it's kind of tedious and pointless, so I'm okay. That's why I didn't actually write it.
What about
AP test, I think you'll be fine if you don't define it.
is that just for the chi or?
That's what I would say just for chi. This is the only time you got that gray area because you're talking about categorical data. So it's kind of, usually they'll prompt you or script you towards a chi-square test. It'll kind of say, what do you think, or perform a test of goodness of fit. So they'll lead you down that. Goodness of fit, you're going to want to identify it here. You can if you want to. I don't think they're going to ding you if you don't. This is the only time I don't think they're going to ding you. Let's see, categorical data. Let's see, expected cell counts. We're going to have to do that in a sec. Greater than or equal to 5. And independent, I can't spell today at all. And random sampling. We're going to assume that because I don't think it was given to us in the context here. Survey was done, so we'll have to assume that third one. Okay? And we need to go find our expected cell counts now. As I told you, expected cell counts is row total times total divide row total times column total divided by the total. So what you need to do is you need to total up all these columns and all these rows. So, for example, this bottom one's 34 plus 9, so we've got, what, 43 there? Do we agree with that?
Yep.
And then we've got 34 plus 49 plus 9 plus 4 plus 5. I don't know what we got there. 18 plus 34. I got to do my calc. Where's my calc out? Let's go ahead and do this. Let's split it up. Let's go. Actually, I'm going to show you guys how to do it. So what number is that? Who's got that number? 101.
No, 124.
This one's what, how many?
124.
124. And now we've got a total of 125 people. That's not right. 225 people. Okay. I'm going to do the first one for expected value. Then I'm going to challenge you guys to do it. To find the expected value for consumers who strongly agree. This is kind of, I told you we're going to have to go to the Wayback Machine and think about connection pieces. Think about when I found the probability of independent events. If we have independent events, don't you get to multiply those probabilities together? Probability that I flip a coin and get ahead, and the probability that I roll a number 6. Isn't that 1/2 times 1/6? Because those are independent events, and that by is 1/12.
Yes.
We agree with that. Do you guys remember that from probability way long ago and I got our way? Yes? Okay. Homogeneity and independence work on that same principle. This total times this total. Consumers times strongly agree. That's 101 times 43. I don't know what that is.
4343.
And now you need to divide that by the total, which is 225. 19.3. Okay. For expected values, it's okay to have decimals. Not so much for actual data pieces. Observed minus expected. Again, expected values can be decimals. Of course, you can't have actual decimals for observed. Okay? Yes? Should be 43 times 101 divided by 225. Okay? So, at this point, here's what I want. We got this row right here, you guys. I want you guys to give me the agrees. This row right here. I want to give you guys give me neutrals. This row right here. I want you guys to give me the disagrees. Fab 3 over here. I want you to give me the strongly disagrees. I will finish up the strongly agrees because that one's already done just about. Okay? I want the expected values. All right, par group. We got values back there? You guys? We got 30.08 and 36 point what? 92. Other two tables, you guys agree? You guys match? You guys match? Okay, this group. We got
14.364 and 17.6356.
Do we match? Do you guys match that? Okay. This group? I know nobody did it here. Since you guys were working back there, we got.
They did do them.
Oh, they did? Oh, yeah. What do you guys got?
14.36.
14.36.
17.6.
So I'll say 7.
17 point what?
There you go.
Yeah, we have 2.9. And 28.1.
That's 27 or 21?
Where?
What you just did, 5?
22.9.
Is it 12.81?
Where? 28.1.
Is that 36.92 or 97?
36.92.
Is it 23 point? That will be 9. Yeah, that one.
23.697. Well, you don't like my handwriting?
What's 23 say?
17.6356. 17.64.
Alright, we're good.
All right. Back to the problem. Do we agree that all expected cell counts are greater than or equal to 5 at this point? Okay. So we also know that we're going to use the chi-square statistic, which is the sum of observed minus expected squared over expected. In this case, do you agree with me that we're going to have a pretty big calculation here? There's a sum of 10 things. Okay? You do not want to write all that out to show your work. So start the pattern. So the first one's going to be 34 minus 19.3 squared. So 34 minus 19.3 squared over 19.3. I'm going to go plus dot dot dot, establish that pattern. I will end, and again this is fine. I'm going to end with 46 minus 28.1 squared. 46 minus 28.1 squared divided by 28.1. Okay? Earlier, when we had the chi-square goodness of fit, wasn't your degrees of freedom, do you need to go down? Wasn't your degrees of freedom k minus 1 or categories minus 1? Last night's homework, yesterday, agreed? Yes? That's a question. Okay. If we're looking at this data today, homogeneity, my question to you is, how many categories are there? Well, there's 5 categories of opinions, and there's 2 categories of people. So k minus 1, do you agree that k minus 1 doesn't really work here? Okay. Degrees of freedom is this. df is going to equal r minus 1 times c minus 1, which is row minus 1 times column minus 1. So in this case, we have 2 rows and 5 columns. Was it 5? Yeah. 5 columns. So we'll have 1 times 4 degrees of freedom. So we'll have 4 degrees of freedom here. I would, again, it doesn't take me about 5 seconds to write that, but it does communicate that I know where I'm getting this number 4 wrong. Does that make sense? I would. All right, now for the cool stuff.
Are we getting?
We're all going to eat our red pills. Right? Red pills means you get to enter the matrix, is that correct? Is that what we decided? Blue pills get you out of the matrix? Okay. So everybody eats their red pill. You need to press the second function and X to the -1. You'll see that that is entering the matrix. This is probably something you haven't done before.
Wait, what'd you say? The matrix. Oh, okay. Oh,
And notice when I touched it, it turns red. All right. We are going to edit the matrix. Go over to Edit. And we're going to edit matrix A. Notice this actually behaves just like your list did. Okay? Hit Enter, and it takes you to a matrix. Okay? The matrix was a 2 by 5 matrix. Remember, dentists, consumers, and then opinions. Strongly agree, neutral, disagree, right? Is everybody okay with how we're getting a 2 by 5 matrix? Because different data sets will give you different matrices. Is everybody okay with that? So you can change the dimensions of your matrix up here. In this case, I'm actually going to type the number 2 just to verify it's a 2 by 5 matrix. And then it will put this into, you have to enter your data. So what is the data piece that is in row 1, column 1? That should be the top data piece. You guys don't have to tell me this because I don't have my form with it. So 34, row 1, column 1. And it will go from left to right. So we need to put, I think, consumers is the top. So what's the next opinion for consumers after 34? What is it? Is it 49? Oh, I already have the data in here? Tells you the last time I used the matrices on this. 9, is that correct? And then 4?
Yeah. Then 5.
And then we're going to have to go, scroll down and have to enter that. And then 5. Can't believe I've used it on my other calc, but not this one apparently. So 9. And 18.
Yep.
And 23.
Yep.
And 28. And 46.
Yep.
Have you guys all entered the same matrices that I've already magically entered?
Wait, what if they were changing?
That should happen. Exit out of that. Exit out. These have matrices on them also.
You don't have to press second on the
Sorry.
No, my home calculator. My soul patch.
Mine's doing A and T.
All right. We've got our matrices. We're doing a chi-square test for homogeneity. So go to Stat. Go over to Tests. All calcs have this one. Not all of them have the goodness of fit. All of them have the chi-square test. Here's the difference between yesterday and today. When you highlight the chi-square test and you go to it, it now says, where is your observed matrices? Yesterday we could only do lists because it was a 1 by something. Agreed? Again, this is the big difference between yesterday's goodness of fit and today's homogeneity and independence. So the default will be A. You're going to always put it in A. It says expected in B. Mr. Wood, I did not put my expected values in B. You did not tell me to do that. Fine. Just leave it as matrix B right now. Go down and hit calculate. We've got a chi-square value of 84, call it 84.5. It should make sense if you have a chi-square of 84.5. Oh dear Lord, that's going to be a very small p-value.
That's huge. All the way -17.
Yeah. And notice that the degrees of freedom is 4 like we had before. So we're going to report our chi-square of 84.5. Degrees of freedom are 4, which gives us a p-value of approximately 0. And we're going to come back and finish the hypothesis test in a second. But here's what I want to do. Chi-square, we got that. Remember, you guys did not put your expected values into matrix B. Watch this. Enter your matrix again. Hit edit. Go down to matrix B.
Whoa.
Really cool things happen. It'll calculate for you when you do chi-square test. The default function.
That's fancy.
So, you need to know, I'll say it again. You do need to know how to calculate expected values. But what's very nice about these bigger data sets, if you know how to use the matrices, then it will do a lot of the expected value work, all of the expected value work for you. Kind of nice, yes? Okay? So, let's finish this up. P-value less than 0, so we're going to go ahead and go P-value less than or equal to alpha. 0 is less than or equal to 0.05. That's going to be reject the null hypothesis. And we'll go ahead and write the conclusion. At the 95% confidence level, there is sufficient evidence to say that the opinions of dentists and consumers is different. And then what are we talking about in regards to advertising? Isn't that what their difference of opinion is? So I'm going to say in regards to, I'm going to cite what their difference of opinion is in regards to level of advertising. Make sure you get both row and column in terms of context in your conclusion. Because they have a difference of opinion in regards to level of advertising, because that's what the question was about. I could do another chi-square statistic and analysis if it happened to be, and I think you guys are with me on this one, the doctor's opinion on how often I should floss and how often I actually floss. Right? How many people have that issue? I mean, you guys go to the doc, anybody go to the dentist and they say, how often are you flossing? And you either lie or you're just honest and they get mad at you. That's me when it comes to flossing. I don't know. Some of you, are you guys good flossers? Okay. So every time you go to the dentist, do they tell you to floss? Yes. So, again, I would expect our chi-square for flossing levels and dentists and us to be even greater than what we have here. Huh.
Wait,
Yes.
the question says test to see if there are intelligence.
Right. We have to assume, remember, we always have to have an equal sign here in our null hypothesis. Our alternative has something besides an equal sign. An equal sign in the context of this problem is saying that the opinion of the dentist equals the opinion of the consumer, unless we have evidence to say that it isn't. And you can see visually on our raw data versus expected value, there's a big difference between the opinions. So your expected result should be a high chi-square value, and it should be a p-value. Okay. We talked about that. The other thing you're going to get, this is your third chi-square. Your third chi-square. Chi-square statistic procedures can also be used to investigate association. The other word you're going to see is a test for association or a test for independence. That's to, not to. Two categorical variables and within a single population. This is now the fine line between today's. This one is going to be also the matrices. So again, I'm going to try to make a little bit of a flow chart. Goodness of fit is always going to be a one row by something columns. Does that make sense in terms of when to use goodness of fit? Is everybody clear with what I'm talking about, one row by columns? Yes? Okay. The one we just did, which was homogeneity. I still spelled it wrong. EI. That is multiple rows, multiple columns. Okay? So I'm going to say homogeneity, multiple rows, multiple columns. And here's the deal. For homogeneity, these are going to be different populations. I'll say it again. Different populations. We're looking at consumers versus dentists. Is their opinion the same or is it different? The third and final chi-square, that's the one we're going to look at right now, is called association or independence. And that's going to be talking about the same population, but with multiple rows and columns. Okay? You might want to make, I recommend you make flashcards about these three chi-square tests, because I have seen it very consistently on free response and in multiple choice. Which chi-square test would you use and why? Okay? Here's how the association or independence will work. Go back. Goodness of fit, homogeneity, or association/independence. Those are kind of the same. These two will use the matrices. This one will not. That's only going to be a one row, multiple columns. That's goodness of fit. These two are related. The homogeneity has different populations, dentists and consumers. The next step, we haven't done this yet, but I'm going to call your attention to it now, so then when I post it up, you'll see that I'm talking about the same population, even though I have multiple rows and columns.
The first one doesn't come up on the GI.
No, but you can do it in lists in TI.
Like dentist one and dentist two. Like board dentist one.
All right, null and alternative are really easy for association, really easy for independence. Null, two variables are independent, or the two variables are associated. Fine. The alternative, the two variables are not independent, or the two variables are not associated. That's also fine there. I would say put it in context. So I'll show you the data set so we can put it into context. Otherwise, it's the same 8. Otherwise, we in a matrix like we just did. Okay? And I want you to look at this data set as I'm reading the problem and see why this would be a test for association or a test for independence and not a test for homogeneity. Remember what I said those two differences were. This table compares whether time spent watching television is associated with cardiovascular fitness. Subjects were asked about their television viewing time per day rounded to the nearest hour and were classified as physically fit if they scored an excellent or a very good category on a step test. Test whether fitness and TV viewing are independent. And so now we're looking at fitness as a variable and TV as a variable. Okay? So we started with the population of students. TV is a variable, TV viewing, and fitness is the other variable. Notice that we have a 4x2 matrix here. Okay? And I will set you guys up with the null and alternative hypothesis, and I would like you to run this hypothesis as top to bottom. The null hypothesis is going to be fitness and TV viewing are independent. Your alternative hypothesis is going to be TV and fitness are not independent. Okay? You guys do the 8-step hypothesis test now with this data set.